This is lesson 3.1a. In lesson 3.1a, we're going to be talking about relations and functions. So when you look at a set of data, a relation is when we put the input or the x-coordinates with the outputs. Those are the y-coordinates. A function, however, is a relation that has exactly one output for each input. And that part is really important. That's why it's bolded. Exactly one output. So each input can only have one output. Each x can only have one y that it's associated with. So one way to determine this is we're going to take this set of data here in example 1, letter A, and we're going to make what's called an input table. Input-output, really. Excuse me. So for letter A, we're going to make two columns. We're going to have our input column and our output column. When you are filling in this data, if the number appears more than once in the input, you only have to write it once. If it appears more than once in the output, you only have to write it once. So we're going to look at each one of these. So my first point I have here is -2, 2. So I have -2 in my input and +2 for my output. My next point, I have -1 for the input and +2 for the output. I already have that here, so I'm just going to leave it. My next point, I have 0 for the input, 2 for the output. So again, already there, I'm just going to leave that. Then I have 1, 0. So 1 is my input, 0 is my output. And then I have the point 2, 0. So 2 is my input, and again, 0 is my output, already there. So what I'm going to do from here, I'm going to connect each input to its designated output. So when I look at my points, -2, 2, -2 on the input matches with 2 on the output. Then I have -1, 2. So -1 input matches with +2 output. 0 input matches with 2 output. And then I have 1, 0. So 1 matches with 0. And finally, 2, 0. So 2 matches with 0 for here. So as I look at this, each one of my inputs, notice how it only has one line coming off from it. So each input matches up with an output. I don't have -2 going to 2 and 0. Yes, I have multiple inputs going to the same output. Totally fine. But each input has to have exactly one output. So it can only match up with one thing in this column. And each one of these does only have one line coming off from it. So because of that, we will say, excuse me, that this relation is a function. Now we're going to take a look at letter B, relation. Again, I'm going to make my input and output table here. So I have the point 4, 0. So 4 is my input, 0 is my output. Then I have 8, 7. I like to go through and put these, excuse me, in numerical order when I put them in my input-output table. So as I look down the row here, I have the next number I would have for my input would be 5, it looks like. And then, so I'm going to check these off. And then let's see, my next input I have is 6. And then, looks like my last input I have is 8. So then I'll do the same for my outputs. So output I had 0. Then I have a 2. And then next I have, looks like 3. And then I have a 4. And then I have 7. All right. So as I compare, the input for 4 is 0. And then for 8, I have 7. And then 6 matches with 4. 4 matches with 3. And then 5 matches with 2. So as I look through, remember, in order for a relation to be a function, we have to have exactly one output for each input. So when I look through this, 8 has 1, 6 has 1 arrow, 5 has 1 arrow, 4 has 2 arrows coming off. So that means that 4 is attached to 0 output and it's attached to 3 as an output. So this means that this is not a function because that input has multiple outputs for that same number. Meaning if I plugged in 4 into an equation, somehow it's going to give me 0 and 3, which would mean that this is not a function for this one. So now we're going to look at another way that we can determine if something is a function. And this method is called the vertical line test. This method works amazing when you have a graph. Now, I could take my data that I'm given, and like these points up here in example 1, I could take these points and I could make a graph with them and use this vertical line test. Most of the time, it's going to be quicker just to do your input-output table. But if I'm already given a graph, I'm going to use the vertical line test. And what that means is that you're going to draw a straight line down through the graph. And if you hit more than one point straight down, then it is not a function. So if we take a look on this first one here, so these dotted lines are symbolizing, I guess is the word I should use, our vertical line. Notice it only hits one dot from this relation on the way down, which is why this one is classified as a function. If I do the same thing on the other one here, so straight down, there are 2 spots on this that are intersecting. So I have one here and I have one here. So 2 spots that are touching that line on this relation. As a result, this one is not a function. And the reason is because our input, our x value, has 2 y values for that relation. That's why this one's not a function. So I'm going to do the same thing on these graphs down here. And I can do it multiple ways. I can actually draw a line. So I'll do that for the first one here. If I draw a line straight down, and since this one's not connected, I kind of have to draw multiple lines. Or maybe I should use a different color. If I draw a straight line, that one only touches one point. This one notice, touches 2. One here and one here. And if I were to continue, it also happens to touch 2 points right here as well. So because I have a spot in this relation where we have 2 outputs for 1 input, we would have to classify this as not a function. Then I'm going to test over here. So I keep drawing all these vertical lines through here. So far, I've only touched the line in one spot for each of my vertical lines. So since none of these lines have 2 outputs for any of these inputs, then we would classify this one as a function. And then for my last one, I'm going to draw. So if I don't want to draw lines, I guess I should show you that one first. If you have a pencil, or in this case, I'm going to use a ruler, then you can just make your straight line and decide, okay, here's my straight line. Is it touching in more than one place? And if we notice, that circle is touching here and down here. So on that one vertical line, I have 2 spots that are touching my line. As a result, this one, not a function. So you can use a pencil, you can use a ruler, you can actually draw those lines. If it's on the computer, sometimes, it's a little bit harder to draw lines. But if you can hold your pencil up or hold a ruler up to see, does it touch in more than one place on that same vertical line, you'll be able to easily determine whether it's a function or not just by that graph. This is lesson 3.1b. In lesson 3.1b, we are going to continue to talk about functions, and specifically we're going to talk about 2 different parts of our functions. So the first part I want to talk with you about are the domain and the range. Basically, the domain and the range are another name for the input and the output. So the domain is the set of all possible input or x coordinate values. Okay, and then the range is a set of output or y coordinate values. So when we're looking at these and we're trying to decide what's the domain and what's the range, we're going to be looking at those x and y coordinates. So in these 2 examples here, we have to find the domain and the range for the function. So if I'm looking at A has dots that are not connected. So I'm going to take the coordinates for each one of these points and I'm going to write them down, and that way I'll be able to more easily find my domain and my range. So my first point is -3, -2. Then I have -1, 0. I have 1, 2. And I have 3, 4. So looking at these, if I'm trying to find the domain, then I'm looking at those inputs or the x value for each one of these. And this little bracket is just to kind of show that they're grouped together. So my domain is -3, -1, 1, and 3. And again, if they happen to show up more than once, I only have to list them one time in my domain. So like if I had 2 -3s, I would only have to write it one time. Then for my range, I'm looking for the output or those y values. So my range would be -2, 0, 2, and 4. So for this one, since they're individual points on this graph and they want the domain, I list all of those x values, and my range, I'm going to list all of my y values. For graph B, these 2 dots are connected to one another. So when I'm looking at the domain, I want to look at what is the smallest value that is graphed here. So on that dot, what's the smallest value happens to be -2, and what's the largest value? So the largest x value is +3. So what that tells me is for my domain, my x value is what I'm working with. And the smallest x value that I had on my graph, remember, was -2. So -2 was the smallest, which means the x is greater than or equal to that -2. But it's less than or equal to that largest value, which happens to be +3. So the spacing for this function says that my x value can be between -2 and +3, and it will fit on that graph that is drawn. But then I have to also look at the range. Range, remember, is dealing with our y values. So this time I have to look at vertically the smallest and the highest. So the lowest number vertically is down here at -1, and the highest value vertically is up here at +2. So just like I did with my domain, my lowest value was -1, so it's greater than or equal to -1, but it's less than or equal to +2. So once I use these domain values and I plug them into the function, my graph would show that the y values would range between -1 and +2. Another set of vocabulary terms that we're going to be talking about in this section are independent and dependent variables. So our independent variable is going to be our input or our domain or x coordinate. All those things mean the same thing. Because basically, if you're going to graph something, you can pick what numbers you plug in for x to figure out which values you're going to get for y. So it's independent. If you think about it, it's kind of like your parents, right? Your parents get to decide what food they buy for the house or what they spend the money on. But the output is what results because of that. So the output is our dependent variable or y coordinate. It depends on what happens with the input. So children are labeled dependents on their parents' income taxes because they depend on the things to sustain that their parents can provide for them. So food, a place to live, things like that. So the dependent variable depends on what happens to the independent variable. So whatever numbers I pick for my x coordinates and I plug them into my function, it's going to determine what my y value becomes. So for example, if we look at this equation right here, if I plugged in 1 for x, I get to choose that I'm choosing to plug in 1 for x. So 1 plus 10 equals y. which is 11. But if I chose to put in a different number, let's say I chose to put in -2. -2 plus 10 would give me 8 instead of 11. So y changes based on what happens to x, and x is something that can be determined. We can plug in those values in instances later on down the road. We'll get to pick some of those x values. All right, so let's take a look at example 2. Water pressure is 0 psi, or pounds per square inch, at sea level. So at sea level, 0 psi, and it increases by about 0.44 psi for every foot an object descends in the water. So it goes down. So the farther you go down in the water, every foot that you go down, those pounds per square inch increase by 0.44. So what this asks in part A, does the situation represent a function? Well, every foot that we plug in is going to increase our psi by 0.44. So if I plug in 1 foot, then it would be 0.44. If I plug in 2 feet, it's going to be 0.88. So every single input has exactly one output. So for part A, we would say that yes, this is a function. And then the second part to this says, if it is, identify the independent and the dependent variables. So if we're swimming underwater, do we get to choose how far underwater we go? We do. So our independent variable would be the depth that we're going underneath the water. The thing we don't get to choose is, depending on how far we go under, that pressure changes, right? So the dependent variable would be the water pressure, because that's going to be determined based on how far you go underwater. All right, so for part B, a whale dives from 1,000 feet to 3,500 feet. Find the domain and the range. So what we're going to do for this one, we're going to make an input-output table. So we've got our input. The middle part here is like the rule. So for every foot we go down, we'll call that x, right? Every foot we go down, the pressure increases by 0.44. We got that from our original problem. And then we've got our output. Okay, so if we look back at the question that they're asking us, they started at 1,000 feet. All right, so let's figure out what the pressure is going to be for this whale at 1,000 feet. So the input that we're plugging in is 1,000. So we have 0.44 times 1,000, because that's that independent variable. And when I do this, 0.44 times 1,000 is 440. So there's 440 pounds of pressure on the whale at 1,000 feet. Then it says that it goes to 3,500 feet. These are below the surface, by the way. So we want to check what the pressure would be at 3,500 feet below the surface. So again, we have 0.44 times 3,500. And 0.44 times 3,500 is 1,540 pounds per square inch. So if I'm looking at my domain, the smallest value that I had was 1,000 feet. So it has to be greater than or equal to 1,000, but it was also less than or equal to that 3,500 feet. So we took our minimum and our maximum, and we wrote an inequality. Then our range, now that we've plugged in those domain values, we look at what we got for the output. The smallest amount we got was 440 pounds per square inch, and the greatest value we got was 1,540 pounds per square inch. So that output, or that range value, is greater than or equal to 440, but less than or equal to 1,540. This is lesson 3.2. In lesson 3.2, we're going to be talking a little bit about x and y intercepts. And intercepts just mean they are the spot where the line from your function touches the axis. So for example, the x-intercept is the spot on the graph where your line touches the x-axis. So right there for the x-intercept. And then for your y-intercept, it's the spot on the graph where the y, or the line touches the y-axis. Okay. So when we're looking at example 1, we are going to estimate approximately where these lines touch the x-axis and where they touch the y-axis. So if we're looking at letter A, the x-intercept for this one, it touches right about there. So what I'm looking at is, first of all, it looks like it is approximately between -1 and -2. So we're going to call it, because we're estimating, we're going to call it -1.5. And remember, when you're labeling a point for the graph, you have to have 2 coordinates. So I went left -1.5, but I went up and down 0. So that x-intercept for A would be the point -1.50. So this is the x-intercept. And we've got -1.50. So that's our point there. For the y-intercept, we're still going to have a coordinate point. But if I go back over here, the y-intercept, it looks like this line here is touching the y-axis right there. And that looks like the point going side to side 0 and up 2. So that would be the point 0, 2 for my y-intercept. And we also have a second graph to look at. So we'll do, I'm going to just abbreviate intercept this time, just to save us some space. All right, so looking at our graph, for our x-axis, it would appear that it's touching in 2 different places. And sometimes you're going to have graphs that do that. Sometimes they might even touch in more than 2 places. So if you're being asked about the x-intercept or seps, make sure that you're looking for all the spots where your line touches the x-axis or the y-axis, depending on this function. So if we have a spot right here, it looks like, oops, I used the wrong color. So we got one right here and one right there. So I'm seeing the point 1, 0 and the point 3, 0. So this one has 2 x-intercepts. Guess I should slide that over a little bit for us. So 1, 0 and 3, 0 for those x-intercepts on that question. All right, now let's go back to the graph and look at our y-intercept. This time it looks like there's only one spot where it's touching the y-axis. It looks like it's right about here. And it looks like that point would be the spot 0, 1, 2, 3, 0, negative 3. So for my y-intercept, I have 0, negative 3. So remember, x-intercept, we're looking where does that line touch the x-axis. Y-intercept, where does that line touch the y-axis. All right, moving on to example 2. First of all, we're going to look at some information right here. So we have different ways to interpret a graph. And we've got positive and negative. We've got increasing and decreasing. And then we've got something called end behavior. So what I want you to notice is when we have positive behavior, it says that positive is when its graph is above the x-axis. So when I look here, they're labeled, but it's this spot there and this spot here. Those are the positive sections. Likewise, we also have negative sections, and that is when it is below the x-axis. So all these spots down here would be considered negative behavior. Then we're going to talk about increasing and decreasing. So if the function is increasing, that's when the graph moves up as x moves to the right. So as we're going to the right, always reading left to right. So as I go left to right, this part here is going up. This part here is going up. Even this part right there is going up. But then if we have a section that is decreasing, that means that it's going down as we go from left to right. So this section here would be considered decreasing because as you read from left to right, it's moving in a downward direction. And then the last part is talking about end behavior. So end behavior is as the x value is going towards positive infinity. Because here's the thing about graphs. They go on and on forever and ever. They never stop. They're lines. Lines just keep going. So if we were to continue this and had infinite paper, right, this line would continue going in that same pattern forever and ever and ever. And these x values would continue to expand forever and ever and ever, like a number line, right? Number lines can go on forever and ever and ever. So as x is going towards what we call positive infinity, so as you're moving right, it's as x goes to positive infinity, what's happening to y? So in this instance here in this graph, as we're moving towards positive infinity for y, or for x, I'm sorry, y is also going towards positive infinity. It's going to keep moving up towards those positive numbers. Likewise, if I were to move the opposite direction, right, if I'm going towards negative infinity for x, so moving on the x-axis towards negative infinity, this time it looks like the y is going also towards negative infinity because it's going to continue to move down in that pattern just the way that we have it right there. So we're going to look at this function in example 2, and we're going to decide positive, negative, increasing, decreasing, and we're going to talk about end behavior for this graph as well. So when I look at it, let's first talk about positive versus negative. So if I have the positive first, remember that it's anything above the x-axis. So I have all of this is above the x-axis. So what I can say for my positive behavior is anything smaller than x, or smaller than x, oh my goodness, when x is smaller than 0, I pointed to it, I said the wrong number. So anytime that x is smaller than 0, we know that we have a positive behavior right here. We also know that from 0 to positive 3 is positive. So I also have a compound inequality. So when x is greater than 0, but less than positive 3, then it is also a positive behavior. I also have negative behavior in this graph. So looking down here, I also have that section right there that shows me positive behavior or negative behavior. So for that one, for a negative, it's anytime that x is greater than 3. So as we're continuing this way, getting greater, this line is continuing to go down. So anytime that x is greater than 3, we have negative trend on our graph. All right, same graph over here, but this time we're going to use it to talk about increasing and decreasing. So when I look at these, I'm going to choose decreasing first. So as I move from left to right, remember, I have this section here, left to right, I'm moving down right there. Left to right, okay, so that's moving up. This is also going down. So those two parts for my decreasing, we're going to have to figure out what those values are. All right, so as we're decreasing, we have anything smaller than x, so kind of like we had with our positive there. So anytime that x is less than 0, it's decreasing. But also, if we continue to look over here, after that point 2, it starts to decrease as well. So we also have when x is greater than 2, we have a decreasing pattern. But thankfully, we also have a positive, or not positive, an increasing pattern here. So that section right there, because remember, as we go left to right, it's moving up. So this would be between 0 and positive 2. So anytime that our, all right, I'm increasing first. Anytime that our x value is greater than 0, but less than 2 on this graph, we have an increasing pattern. All right, so now we also have to talk about end behavior. So remember, end behavior is all about what's happening to y as x approaches positive infinity, and then what happens to y as x approaches negative infinity. So if I'm looking at this graph, as x is going towards positive infinity, it looks like our y values are going down. So those y values are approaching negative infinity. So the way I'm going to write it is y, and this arrow means is approaching negative infinity. Looks kind of like an 8 on its side, that's infinity symbol. So y is approaching negative infinity as x is approaching positive infinity. So as we're moving up on our graph on the x-axis, this y value is decreasing, it's going down towards negative infinity. Now let's look about what is happening to y as x approaches negative infinity. So as x is approaching negative infinity, so we're continuing down our x-axis here, what's happening to our y? Well, it looks like it is approaching positive infinity because it's continuing to move in an upward pattern. As x goes down, y is going up this time. And example 3. Example 3 says, researchers send 2 robots to explore an asteroid. The robots move by hopping between locations. The graph shows the path of robot A's first hop. Robot B lands 60 feet from where it starts its first hop, reaching a maximum height of 48 feet after traveling a horizontal distance of 30 feet. And then we have to compare those 2 hops to one another. So, for starters, this robot is starting, just like the other one, at 0, 0. Oops, not the one I was thinking of. So it starts here at 0, 0. We know that it lands 60 feet from where it started. So 60 feet away is where it landed. And it says that it reached a maximum height of 48 feet after traveling a horizontal distance of 30 feet. So basically that makes it the point 30, 48. So on my graph, I'm gonna go over to 30 and up to 48. And I'm gonna have to estimate this because it's not an exact, because this line here is 50. So it kind of looks like that. Let's give robot A some color so we can see that better. All right, so if we want to compare these 2 things, a couple things we could look at first of all are those x-intercepts. So they both started in the same place at 0, 0, but one of them landed what would appear to be at 45 feet, and one of them landed at 60 feet. So if we wanted to compare these 2, we could do our 60 feet, which was robot B, minus the 45-foot distance of robot A. So we know that robot A had a 15-foot shorter hop than robot B. Remember, those are those x-intercepts that we used. I'll just put a little reminder here for ourselves. We also could take a look at the heights that we have, right? So it looks like, well, we know robot B had a height of 48 because they told us that specifically in one of our measurements. For robot A, we're kind of estimating, and it looks like it's between 50 and 60. So we could estimate that to be about 55 for robot A. So robot A was at 55 for their height, while robot B reached a maximum height of 48 feet. So that means for this one, we had a 7-foot higher jump for robot A, or I guess they called it a hop. 7-foot higher hop for robot A than robot B. And this was our max height that we were comparing. So when you have graphs, you can pick different aspects of them to do your comparisons. So for this one, we use our x-intercepts here, and we also use our max height of those 2 graphs to kind of make some comparisons between the 2. So if we think about it, I mean, robot A landed short, but they got higher off the ground, while robot B got farther away, but less height off the ground. So depending on what they're trying to use these robots for, it could help them determine which one they would want to use based on that result.